So we have covered the earlier floating point addition, also how to write the floating point format. We would like also to cover floating point, basically, multiplication. Suppose that we have now decimal numbers. That number would like to multiply by that number. Of course, as we have done in addition, we need to follow some steps. Also in the multiplication, we need to follow also some steps. The very first step is add exponents. Of course, I need to add the exponents. Here, the exponent is 10 minus 5, or 10 plus minus 5, it is 5. And then we need to multiply the significance, meaning I would like to multiply this number by that number. If you do the multiplication, you will find that is the number, and then multiply it by whatever the exponent that you had. Then I will normalize the results, meaning I will put it in the scientific notations, 1 point something multiplied by 2 to the power of something, or here, since it is decimal, multiplied by 10 to the power of something. Check if there is over or under flow in this case. If any, I just need to round and normalize if necessary. And then we'll determine at the very end the sign. Since this is positive and this is positive, positive multiplied by positive is positive. So at the end, that number will be positive, and I'll just take the number that I had here with me. Can do also the same things exactly if I would like to multiply floating points binary numbers. Suppose that I would like to multiply 0.5 by that number. If you recall, these were the two numbers that I had in the addition earlier. We have shown you that actually 0.5 is that in binary, and that number is this in binary. Again, we need to follow a certain particular steps in order to do that multiplication. Let's go over this step by step. So here, suppose that I would like to do a floating point multiplication. Suppose that I would like to multiply 0.5 by minus 0.4375. If you recall from previous calculations, we had shown that this is basically equal to that number. And we showed that this is equal to that number. The very first step is basically add the exponents. So here I have the exponents -1 and -2. So basically I would like to add -1 plus -2, which will give us -3. Second, multiply the significant. So I would like to multiply that by that. Let's do this multiplication then. So it is 1.000 and then 1.110. Just do the multiplication. 0 multiplied by all of these will give you zeros, and then 1 multiplied by that will give you that, and then 1 multiplied by that will give you that, and so on and so forth. So let's begin this calculation. Then the 1 will give you the same number. And then the next one will give you the same number. And then the last one will give you the same number. And then just do the addition. This is basically will be 0, and then 0, 0, 0, 1, 1, 1. The question is where to allocate the point. The same things exactly as you have learned earlier with just the decimal multiplication. When you do that, you calculate where is the point in this, where is the point in that, and add both, and then allocate that here. So this point, suppose that it moved left by 3. So this is after 3 digits. This is after another 3. So this means that after 6, this is what we will do: 1, 2, 3, 4, 5, and then the, sorry, it was here. So 1, 2, 3, 4, 5, 6. So basically, I need to allocate the point here, and that's why that number is like that. So basically, the number that I have is this multiplied by the exponents, which is 2 to the power of minus 3. So my number right now is 1.110 multiplied by 2 to the power of negative 3. 3, normalize the sum. Normalize the sum meaning I need to put that in the format of 1 point something multiplied by 2 to the power of something. Interestingly, this is what it is right now. So it is exactly the same number, 1.110 multiplied by 2 to the power of negative 0. When you check that, you will find that there is no overflow or underflow since the number here is written in 4 digits. Why we mentioned that 4 digits should be okay? Because each of these digits needs to be written in 8 bits, correct? So 4 multiplied by 8, 32 bits, and we assume the register is 32 bits. That's why 4 digits supposed to be like enough for me in that particular case. And if I'm not exceeding that, then it should be okay. So just to normalize the number, if there is no overflow or underflow, then that should be okay. If not, then we can normalize. So in all, we can round. So in all cases, round the sum. In my case, since there is no overflow or underflow, it's already 4 bits. So basically, my number will be the same. And then the last step is set the sign. If you see here, this is positive, this is negative. Positive multiplied by negative, I should get a negative number. And that's why I am expecting that basically the number will be minus 1.11 multiplied by 2 to the power of negative 3. So this is the multiplication. How I could know that this multiplication is correct, or how I can check? We need to make sure that multiplication is basically correct. How we can do that? Let's take that number and do that multiplication minus 1.11 multiplied by 2 to the power of negative 3. That means basically that points need to move 3 to the left. So try to write that number in this case when we check. So it will be minus 0.00111. Okay, so that number we mentioned earlier that we can have a trick on writing that number in that way. You can have 111 divided by 2 to the power of 5. Why? Because we have assumed that the point is here. And if I write 111, the point is here, divide by 2 to the power of 5, meaning that the point have moved 1, 2, 3, then 4, 5. So add 2 zeros, which is that one. So this can be written as that. 111 divided by 2 to the power of 5. But this is written in binary. I need to write that in decimal. So that basically is equal to 7. And 2 to the power of 5 is 32. Of course, this is minus, so this is minus, minus. Minus 7 divided by 32 is minus 0.21875. By the way, if you check that and do the multiplication between these, you will find that it's equal to that number. If not, so this means, of course, that you have done certain mistakes in the steps, and you need to review and see like what's exactly the mistake was. So floating point arithmetic hardware, for the floating point multiplier, for instance, it is similar in complexity to the floating point adder, but here we'll use multiplier of significance instead of just adding them. Floating point arithmetic hardware in general can do addition, subtraction, multiplication, all of these kind of things, if you will. Again, you don't have to think about the blocks in advance. What you need to think about is basically what's exactly the function. You can write the function in a flow chart, and after you have the flow chart, you can easily transfer that to a hardware description language. It can be through Verilog or with other options, VHDL, for instance. Can do also a floating point to integer conversion. This shouldn't be that difficult. One of the drawbacks of the floating point that it takes several cycles, but the good things that we can actually pipeline that so it will be a bit faster than normal things. Other things that we mentioned earlier in summary, but here we will just go over it a little bit in details, that some of the values of the exponents basically are reserved, and also with the fractions. Let's see like how we can interpret these kind of things. If the exponents all ones and the fractions all zeros, we'll assume that this is plus or minus infinity. If the exponents all ones and the fractions not zero, so this is basically not a number, and so on and so forth. Here will be given a table as an example, and we don't expect that you remember these kind of things. For instance, with whatever we mentioned, if the exponents in the single precisions are all ones, which is 255, and the fractions all zeros, so this is basically plus or minus infinity. For instance, of course, of all ones in the double precision, since I have 11 bits, so this will be my number, and zeros again plus or minus infinity. If all ones, but this is non-zero, again, this is not a number. Of these zeros, this will be zeros, and so on and so forth. So here, everything is written in that table, and we don't expect that you will remember these kind of things. It will be given to you if needed. So let's see how we can do actually floating point instructions in the MIPS format. One important thing to highlight that in the MIPS, we have separate floating points register file. So we have from F0 all the way to F30 first. These registers can be used in pairs or in double precision values, as we will explain shortly. So suppose that I would like to use a load word or a store word. This is what is the syntax in this case. So if I would like to do a load word, I need to use that syntax. And basically with the same concepts that I will go to that particular place, I will open whatever in S2C, whatever the address, and then add 54 to that address. So now I know that this is the location in the memory that I'm targeting. I will take that location and copy it to register F1 in this particular case by loading load word. I can do the opposite case if I would like to do a store word from the F1 to a certain particular address. In this case, I have to go to slot S4, see what is the address there, add 58 to that particular address, and then I knew now the place in the memory that actually I will store the word or copy whatever in the F1 to that particular location. In addition, I can do also other arithmetic operations. Suppose that we need to do an addition. I can do addition in the single precision, and I can do addition in a double precision format. In the addition on the single format, I will use .s. I will write F2, F4, F6, for example. That means that I will add whatever in these two registers, F4 plus F6, and then the results will be allocated in F2 in that particular case. If I will try to do the exact same things, but in the double format, meaning that I will write add.d F2, F4, F6. But in the double format, I'm using a 64 bits instead of 32 bits. However, all of these registers in 32 bits. So how we can deal with that? Interestingly, as we mentioned, we can use these registers in pairs in double precisions, meaning that if I will write F2, F4, F6, we will understand that F4 meaning that the F4 concatenated with the next following register, which will be F5 in this case. And the F6 will be concatenated with the next following registers, which will be F7 in this case. And this will be added with that. We expect that the results will be or has to be written in 64 bits. And that's why it will be written in F2, but F2 is only 32 bits. So again, with the same concepts, it will be F2 concatenated with F3. Similarly, with the sub or multiplication or division and so on and so forth, you can use this in the single format and this with the D or in the double format, as you can see here. Also, we can use that in some other floating point instructions. Suppose that we would like to do a comparison, for instance, will be written in that C.X.S. So this is S for single format. X can be any of these. can be equal, can be not equal, can be less than or equal, greater than or greater than and equal. Then I will check, for instance, if it is less than, if F2 is less than F4 or not. If yes, the condition will be equal to 1, else the condition is equal to 0. So that means that I can also do that instead of single precision, double precision. But suppose that this is the case with F2 and F4, again, because this has to be written in 64 and this has to be written in 64, so I will concatenate F2 with the next following one, which in this case will be F3, and the F4 will be concatenated with the next register available, which will be F5. Again, I will check if this is concatenated with this is less than this concatenated with this or not. Then if yes, condition will be equal to 1, else condition will be equal to 0. And assuming I have a branch operation, and I would like actually to branch if true to that particular location, meaning I will check the condition. If that condition is true, is equal to 1, then please go to that particular place. But since we already mentioned that in the branch there is a certain particular rule we need to follow in order to know the next address, it's just relative address. So it will go to that particular relative address by program counter +4 plus the 25 in this case. You can also branch if false, meaning if condition is equal to 0. So this means that you will go to program counter +4 plus 25 with a similar case. Let's take an example in how to transfer a C code to floating point format. Suppose that we have this higher level code that we have defined as floating point with this name, and we would like to transfer basically between two types of degrees. Let's say that we choose the Fahrenheit here and Celsius, and this is the equation basically for that transfer. I'm giving you here that the Fahrenheit, that variable, is in F12, and the results has to be saved in F0. And we need to know how I can write that particular code in MIPS in that particular case, given that these are floating point format. Interestingly, it has a little bit of different syntax than the usual case. So the very first thing that I need to think is how I can allocate these values, the 5 and the 9 and the 32. That means that actually I need to load word that particular number in a certain particular register, and that particular number to a certain register, and that particular number to a certain register. How we can do that? Interestingly, this is an example of how to do that. Load word 5, I will write as a constant 5 from the global pointer to F16. So that means that F16 now is equal to 5. We'll do the exact same things with constant 9, but it will be saved in F18. So now this is in F16, this is in F18. The next step is just to do the division. So I need to do the division of F16 divided by F18. So F16 will be divided by F18, and then I need to put the results in another register, or I can override any of these registers. In that case, I have it chose to override F16. So we will divide F16 by F8, meaning divide 5 by 9, and then I will override the F16. And remember that here I'm using a single precision. Okay, so I have finished that, and the results now in F16. My next step is to think about that with the same exact concept. This 32 will be saved in a certain register. We will call it F18. As you can see from here, this constant 32 will be saved into the F18. And after that, we need actually to subtract that 32 from a variable Fahrenheit. Fahrenheit here, as we have given, it is saved in F12. So basically, I would like to subtract F12 minus F18, and this is what exactly I have done here. F12 minus F18, and then put the results in a certain particular register. I can choose different register, or I can override my F18. I can choose that. In this case, we have override F18, so F12 minus F18 is now in F18. The very last step is F18 multiplied by F16, which is here. Multiplied with a single precision, F16 by F18 we need to allocate that in a certain particular register. I cannot choose any register if it is not given, but in this case, it is given that actually your results has to be in F0. And that's why this final multiplication with this F16 multiplied by F18, it has to be saved in F0. And then as usual with any other function, as soon as I finish the function, I have to jump to register to return address register, meaning that I need to know where exactly to return after I have finished my function. So with these examples, we already knew like how to write something like that in two MIPS. Now let's try to switch the gear to also another property with the associativity property, and we need to double check if the associativity property hold in the floating point format or not. Suppose that we have three numbers, x, y, and z. This is x, this is y, and this is z. And we would like actually to add x plus y plus z. But first, I would like to add x plus y at the beginning and then the results to z. Or I would like to do y plus z and then the results to x. And we would like actually to compare the results. Are they equal to each other or not equal to each other to see like if the associativity hold or not. Let's begin with the very first option here, x plus y first, and then we'll add the z. X is that number, y is that number. As you can see, it's exactly the same number. The only difference is the negative sign. If I'm adding x plus y and they are exactly the same, of course, the results will be 0. Yes, number plus minus the same number, it's exactly equal to 0. And then the results is 0 plus z is equal to 1. So 0 plus 1, the results is equal to 1. So my results is equal to 1 in this case. Suppose that I would like to do y plus z first, and then the results will be added to x. In this case, this is the y plus the z. That number added to that number. As you can see from here, this is multiplied by e to the power of 38. Huge number. Added to 1. A huge number added to 1. What will be that? If you would like to add billion plus 1, what is the result? Billion, correct? Yes? If you have like to add 1 to the power of whatever, 38 plus 1, it is just that particular number. So when you add this with that, you are just getting the same number. Then this is the results of that added to x, which is added to the same number with the negative sign, which is at the very end is 0. So as you can see from here, that actually it doesn't hold that you will always get the same number. You have to be careful from this kind of things. And this is usually one of the basic mistakes that you may fall in when you do multiplication or addition in a floating point format. Another thing we would like to highlight, we covered earlier, but we didn't go that depth if we have assigned number. Just to remind you about that, if you recall, we mentioned that there is something called right shift or left shift in either if I would like to do division or multiplication. Left shift by I places, multiply an integer by 2 to the power of I, or right shift by 2 to the power of I, meaning I would like to do the division and so on and so forth. We have seen how to do that earlier. Just shift left or shift right, meaning either multiply or division in this particular case. But all of that, basically, we have explained regarding unsigned numbers, not signed numbers. So what will be the case if we have a signed number? Can we do the same concepts? Can we shift by 1 or 2 and then we expect multiplication, or can we do shift left and then we expect division or not? Let's see that example. Suppose that I have a negative 5, as you can see, a signed number, divide by 4. I would like to divide by 4. Let's write minus 5 as an example, or negative 5, and then, or that number, and I would like to shift right by 2. Okay, shift right by 2. That one will be shifted by 2. These ones will be shifted by 2, so of course it will be removed. This 0 will appear here. So just shift all of these by 2. I'm expecting, of course, if I shift all of these by 2, that there is 2 spaces here. I will add zeros. Shift left by 2, all the numbers, just shift left. So of course, I'm losing these 2, and I'm adding 2 zeros to the left. So now this is the number after the shift. Can you read that number? That number, unfortunately, is that large. So I didn't divide -5 by 4 in that sense. Why? Because this is signed. How we can solve this issue? Oh, we mentioned that you need to do what we call arithmetic right shift in this case. What does arithmetic right shift mean? Arithmetic right shift means that I would like to extend the sign bit instead of just shifting to the 0. Meaning that this one, yes, it is shifted by 2, but in this case, I will extend the sign number in this case. What is the sign bit? It is 1. So basically, I will extend the sign bit in this particular case. So the shift is occurred. This 1, 1 already removed. The 0 came here. The 0 came here also. But the other two numbers that I had to add is just an extension of my sign bit. My sign bit was 1. So it is extended to 2 ones. And then read that number. When you read that number, you will find that it is equal to -2 as an example. If you do -5 divided by 4, -2 is a lot closer than that number. So although you didn't get the exact division that you are intended to, but a closer number to that particular intended number in this case. So the idea of the signed numbers, when we asked you to do a shift, is basically an arithmetic shift. You can apply the same things if you have the sign as zeros, because if you have the sign as zeros, it's just the normal case when you will extend that zeros to the left, so it is just unsigned number, if you will. And it will be the same case. Just a revision to whatever we have covered in this chapter so far, the overflow, which happens when a positive exponent becomes too large to fit in the exponent field. Also an underflow, which happens when a negative exponent becomes too large to fit in the exponent field. So either too large, it will be overflow, or negative exponents, again, too large, again, it will be an underflow in this case. We mentioned also with the IEEE format that it will be -1 to the power of sign multiplied by 1 plus f multiplied by 2 to the power of e minus bias. We can have the format for both single and double precisions, as we have explained. The most important thing is that f is stored in a normalized format because there is a hidden one. Because when we write the f, the fraction, we know that there is a hidden one there. That's why we add the 1, as you can see here, 1 plus whatever is there in the fraction. And to simplify that, the floating points e, the exponent, is represented in excess or bias notation. Remember this expression because we will come to that in one of the review questions. Excess, meaning bias. Notation where the bias, as we have mentioned, is this number in the single or that number in the double format, meaning that the most negative will be, in this case, will be that, or the most positive will be that, as we have explained earlier. So now we have covered a huge amount of information regarding like the assembly, integer, floating points, how we can deal with all of these things. We need now to think about the next step is the CPU implementation. How basically we can implement that. We'll see like how we can do that in a simple format, and we will also see how to do that in the pipeline format. And when these two formats will cover like a store word, load word, how we can access the memory, how we can access the register, all of the steps needed from the very beginning of entering just the zeros and ones to the CPU, and then output whatever like the execution that we would like to get. We'll see all of the steps in details. But just conceptually, if we were to think about now, we have a code. We have a certain particular instruction. What we need to do next? Of course, the very first thing that we need to think about is to grab that instruction, correct? Meaning fetch. So the very first step is fetch that instruction. Okay, so now I have it in my hand. I fetch it, I have it in my hand. What I am expecting the next things to do? The very next things to do is to read that instruction and decode it. Because I need to understand what that instruction is basically requiring me to do, correct? So now I have the instruction. then I have decoded, so I have already knew what is exactly the meaning of that instruction. What would be the next step? The next step is just to follow the instruction and execute. So the very first thing is fetch, grab, and then decode, and then execute. It's exactly the same things in just a normal life. You have any order, the very first thing is to take the order, then read the order, and then follow the rules in order to execute the order, correct? Here's exactly the same. But one of the things, just like to remind you that these instructions should be allocated in a certain particular space, or basically a place. In that sense, of course, we expect that all of these instructions are allocated in the memory. But as we will see later on, that actually we can think or separate the instruction memory from the data memory, meaning that all of the instructions will be held in the instruction memory. All of the data will be held in a data memory. Nevertheless, all of these still in the memory. Okay, so again, the very first things, as soon as I will see my code, the very first thing is basically to fetch my instruction. And the most important things to remember that as soon as I fetch, I would like to make sure that my pointer or the next address to be executed is in the correct place, meaning that my program counter right now is pointing out to the next instruction to be executed. So this is the instruction. I will fetch that instruction. As soon as I will fetch that instruction, I would like my pointer or program counter pointer to point out to the next instruction to be executed. Why? Because as soon as I will fetch that, I will decode and then execute. And after I finish, where to go afterwards? I need to know where to go by that. So I need to go to fetch the next instruction, that one. That's why here, as soon as I fetch, I do an addition +4 to my program counter. Why +4? We have explained a lot earlier why +4, because this +4 may change it according to our design. But suppose that my memory has an 8-bit width and my total bits in 32. So basically I need 4 slots, and that's why it has to be shifted by 4. And then I will decode that instruction, and after that I need to execute. So all instructions except the J will use the ALU, arithmetic logic unit, after reading the register. And we will explain that in detail. So just for your reference, we have here our instructions. Again, it is in the instruction memory. I will keep fetching one by one. So as soon as I fetch that instruction, it will go to see like what I will do with decoded and then executed and so on and so forth. And as soon as I will have that, my program counter, of course, has to be updated with program counter +4. But there's an important things we need to highlight here. And as you can see from these connections, we have a connection here, a connection here. For instance, I have inputs and then outputs. As an example, I have inputs, then outputs. So if we would ask ourselves that line, if this is the output, so which input it will take? Will it take that input or that input? Or here, that output, will it take that input or that input, for instance, and so on and so forth. Implementation-wise, we can't have connected wires like that. We need to add a components in between to specify which will be available at the output and the when. In that sense, basically a multiplexer will be solving that problem. So basically, we'll add here a multiplexer, we'll add here a multiplexer, we'll add here a multiplexer, as you can see from here. So now I have a multiplexer, have the inputs. For instance, I have the output and then a selector here. So as soon as I fetch my instruction, we'll have that, of course, to a certain control unit. With this control unit, it will specify when to write a register, also specify that multiplexers, also when to write and when to read and stuff like that. And of course, it will help also in decoding all of these and see like what exactly I need to do at that particular situation. Meaning, take the instruction and begin to decode that particular instruction. Suppose that we would like to do that manually. How we will do that? We expect that that instruction will will basically fall under any of these types. It can be either an R type, or it can be an I type, it can be a J type. I am expecting, of course, that you will remember the formats of all of these: R type and J type and I type. As we have mentioned earlier, if we will begin to count from here 0 all the way to 31st, so basically the last 6 bits in all of these is basically the opcode. So basically I will go to check the very last 6 bits in this opcode. As an example, if I found that this is 0, the opcode is 0, I know, for instance, that this is an R type. And then the very next step is to check the function, meaning the very first 6 bits in this case, and see like what's exactly the function. Accordingly, I will control my register and I will control my ALU, arithmetic logic unit. If, for instance, from that opcode, I know that it is belonging to the I type, so I will know that the next will be RS, the next will be RT, and then the 16 bits here will be the address offset. So it can be a certain address, or it can be the offset, or if I have a branch, then I will deal with that at the program counter plus 4 plus that address, and so on and so forth with each one of these. If I have already knew that this is jump, I will know that all of these will be the target address. Meaning, as you can see from here, the RS is usually from 21st to 25th, as you can see from here, and there. The RT is from 16 to 20. The RT is from 16 to 20. The RT will be 16 to 20. If it is an R type, I will know basically that again from the 11 to 15 will be the destination address. Otherwise, I will know that this is either an I type or a J type, and I will allocate that to a certain particular way of interpretation. This will be just exactly what we have done manually here. We should be implemented automatically, meaning that we will write a code that will take the instruction and will begin to do all of these steps. Look at the very last 6 bits, see what is that, and so on and so forth. We'll give some examples later on in how to handle this kind of things in very log. So just for your reference with logic design basics, you can have logic low voltage as 0, high voltage as 1. We can have this a combinational element, or we can have a sequential element or a state elements. Of course, if we have a sequential or a state elements, that means that I need to use a flip-flops. One of the famous flip-flops, as we will see, or I will review later on, the D flip-flops. But before we go to that, let's see the combinational elements. Suppose that we would like to do an AND gate as an example. So that's Y will be just A and B. I have A and B as an input. Y will be A and B. Or I can have an adder, A and then plus B. So Y will be A plus B. Or I can have a multiplexer, meaning the Y will be equal to this if S is 0. Y will be equal to that if S is equal to 1. By the way, this is how I would write that in Verilog. This is the way that I would write something like that in Verilog. Or I can have a function, meaning that I have this input as an A, this input as an B, and Y will be a certain function between A and B, and I will define that function, as we will see later on. I need to define that function. I need to write, of course, the code in Verilog to specify what's exactly the function. But the addition, as an example, is something common. The multiplexer also is something very common. Suppose that we would like to represent that in a sequential elements. With the sequential elements, we need to use a D flip-flop. So this is a D flip-flop. And the D flip-flop is not but having the input appear at the output at a certain particular trigger, for instance. If I have the trigger as a clock, I can choose, should I follow the rising edge clock or the falling edge clock? Meaning that I will transfer the input to the output at a certain particular edge clock. Meaning, maybe I will choose a rising edge clock. So as soon as I have a rising edge clock, I will transfer the input to the output. Others will choose the falling edge clock. So as soon as I will have a falling edge clock, I will transfer the input to the output. In another sense, you can think of this as a D flip-flop that is yourself, that you're just closing your eye. And you open your eyes at a certain particular situation with this trigger. Suppose you chose that it will be a positive edge clock. As soon there is a positive edge clock, you will open your eyes, and then you will transfer the input to the output. Then close your eyes again. Then open it at the next positive edge clock. As soon as there is a positive edge clock, you will open the eyes, transfer whatever in the input to the output, and so on and so forth. If you will choose that as a negative edge clock, so again, you will close all of your eyes. As soon as there is a negative edge clock, you will just open the eyes, transfer whatever in the input and the output. Other than that, any changes in the input will not appear into the output unless you open your eye. That means if it happened that to be changed in between, this will not be transferred to the output. That's why we call it sequential. It is just sequential, meaning that it will not appear at the output unless there is something control that. In that sense, it will be the clock. It can be a positive edge clock or a negative edge clock. Suppose that here is a positive edge clock. I will open my eye. What is in the input? Then it will appear in the output. In that negative edge clock, as you can see, that didn't change because I didn't open my eyes. I didn't see any change. With this positive edge clock, again, there is a change, or there is whatever I have here, it will appear at the output. Negative positive edge clock, again, it will appear at the output, and so on and so forth. But I may even have a more controller over that you will not be able to open your eyes until you have a right signal or a right enable or an enable signal. An enable signal will say like, hey, now you can open. And then when you open, see if there is an edge clock or not. This is with this right signal. So this is my clock, and this is my right. As we mentioned, you will not open your eyes unless this right signal is enabled. Meaning that if it is enabled, then you are allowed to open your eyes when it is edge clock, positive edge clock. So if it is positive edge clock, whatever in the input will appear in the output. Then the right is actually disabled. So though I have a positive edge clock, my eyes is still closed. So whatever is here is not transferred to that. It just is as it was. So if that number is changed, let's say 7 or whatever, this was 6, I haven't seen that. It's still with these old values. Again, my right is enabled. So as soon my right is enabled, with this enable, there is an edge clock. I can open my eyes here, and whatever the value is here, I can then transfer to the output. Sequential meaning it's just control when the input will appear at the output. It's not like the combinational. With the combinational, if you have an AND gate as an example, as soon as the input changes, the output changes. But you have a sequential, then you are controlling. Your input might be changed and the output still as it was because of the clock. And this is you will control, of course, over your design with the micro CPU. So with this clocking methodology, you might have a state elements or an edge trigger. The state elements, so here I have a combinational logic. A state element, you are just using that without any control of the clock. But if you have a clock, then you might have like a state element 1, you might have a state element 2. Between them, you can have a combinational logic, and you will move from state 1 to state 2 only when you have a positive edge clock. So here you will look at the input, and then you transfer to the output. Then you will do some combinational, you change actually the input. You will transfer that to the next state only when you have another edge clock, and so on and so forth.